to lead you through the next session. And before I do that, I want to thank you very much. I want to thank Mario Storga for the really nice conference dinner yesterday evening. He did a great job, he and his team. So Mario, thank you very much for this really nice evening. Yes, and now I have the great honor to introduce Professor David Rosen, one of the godfathers of 3D printing. And I want to give you a short overview about his bio. David Rosen is a principal research scientist at the Institute for High Performance Computing and the Singapore Institute for Manufacturing Technologies. Both are A-star institutes in Singapore. He was a professor in the School of Mechanical Engineering at the Georgia Institute of Technology for many years. Additionally, he held faculty and research positions at the Singapore University of Technology and Design. He received his PhD at the University of Massachusetts in mechanical engineering. His research interests include computer-aided design, additive manufacturing, and design methodology, with a special interest in design for additive manufacturing. He is a fellow of ASME. Also, he is the recipient of the 2013 Solid Freeform Fabrication Symposium and more awards. And in the standards community, he chairs the ASTM F42 subcommittee on design for manufacturing, for additive manufacturing. So, Professor Rosen, I'm very excited for your presentation. Please start.
All right, thank you very much for that kind introduction. Really thank the Design Conference organizers and the Design for Additive Manufacturing Special Interest Group for inviting me to come back to Croatia and Dubrovnik and have the honor of giving one of the keynote talks. Right, so as Professor Wartzack said, right, I'm actually in Singapore. Well, I'll get to that in a minute. And yes, spent most of my career as a mechanical engineering professor at Georgia Tech. So a little bit of background on what is this Singapore A-Star thing. So A-Star is the Agency for Science, Technology, and Research. It's basically the national labs of Singapore. So it's very broad, Science and Engineering Research Council, Biomedical Research Council. And just to give you a little perspective, there's about 5.5 million people in Singapore. It's a fairly small island. And there's about 4,500 technical people that work at A-Star. Okay? So in Singapore, they do take research very, very seriously, and there's lots of support. I'm part of 2 of the 18 institutes in A-Star, IHPC and SimTech. And there's roughly 450 or so technical people in each of those. Right, so what I'll talk about today, design for additive manufacturing. It's great to see several sessions here at the conference on design for additive. Last time I attended physically the design conference in 2018, I'm not sure that there were any. Really good growth and interest in this topic. The other topic that's really grown a lot here at the conference is AI and large language models, but I will not mention either of those topics in the rest of my talk. Yeah, so we'll talk about design for additive, give a bit of an introduction. We got to expand that to the process chain. And then I want to tie a lot of this design for additive stuff to sustainability. That's one of the themes of the conference. And then, time permitting, I'll say a few words about product architecture, design, and 4D printing. But just to provide a good foundation for everyone, right? Additive manufacturing or 3D printing represents a class of 7 categories of processes. They're all listed here. I won't go through them in detail, but they're all based upon the principle of basically layer-wise adding and processing material to build up parts. Okay? They all share that kind of characteristic. They vary in terms of the material type, how the material is processed, and things like that. But you know, that broadly, that is the class of processes. And just to, again, provide a little bit more of a grounding, I've got videos of 3 different processes here, metal powder bed fusion up there, and let me see if I can start these other guys. Metal directed energy deposition is up here using essentially a welding head on a robot arm. And then what many of you know of as 3D printing, or Stratasys' FDM, is the deposition of thermoplastic polymers, filament, basically, to build up parts. Okay? So laser processing, thermal processing of polymers, and a variety of other kinds of approaches here are used. Okay. The thing that sets apart design for additive manufacturing from design for manufacturing is basically there's an opportunity to really make use of the unique characteristics of additive manufacturing in a way that's not so apparent with conventional manufacturing processes. I'll say a little bit more about that. So my definition of design for additive is to try to maximize product performance through the synthesis of shapes and sizes and material composition and microstructures and things like that. Really take advantage of the unique capabilities of additive. And yes, we have to deal with the limitations of the processes, but let's really emphasize what the opportunities are. What are the unique characteristics of additive? Well, they're listed here. Shape complexity is the most obvious one. If you're laser processing the material, the laser doesn't care how complicated the part cross-section is. It'll draw it. Likewise, if you're extruding thermoplastic filament, you can extrude it in virtually any shape that you want. Material complexity. A lot of these processes will support multi-material processing. So parts can be made of more than one material, and we can also functionally grade materials or mechanical properties. Hierarchical complexity basically means features can have features, so we can texture, or we can put texture on surfaces, or we can basically have lattice structures composed of lattice structures and things like that. And then functional complexity is the idea of building mechanisms or working devices right in the vat or in the machine, illustrated by this example, which is the elevator in a stereolithography machine that was made in a stereolithography machine, where there's about 6 or 7 different metal components that were inserted into the vat, in the liquid resin vat, and the rest of the structure was built around them. Plus, there are some kinematic joints here, so the elevator slides up and down on a couple of shafts, and there's other stuff we built in there. But the point is simply that you can get working mechanisms if you can get the material out of the joints and support structure out of the joints, things like that. You can also embed, in some cases, motors, actuators, printed circuit boards, and things like that right into the machine and build around them to make functional devices. All right. People have been really creative about taking advantage of these unique capabilities to do really amazing things. I've got a mix of technical artifacts here, as well as some other non-technical things like this. But the fashion industry, jewelry, people have been amazingly creative in what they've done. The American football helmet shown over here is a really good example of taking advantage of shape complexity capability to make custom designed parts. This is a spinal implant from Stryker, again, taking advantage of shape complexity capability. Hearing aid shells, Invisalign aligners, custom designed devices where, 1 million of those invisible aligners will be produced per month. Right? You can't do that using other manufacturing processes. So if we think a bit broadly and try to collect everything together, we can come to this distinction again between conventional design for manufacturing and design for additive. And so in conventional design for manufacturing, what that usually means is let's understand all the limitations of the manufacturing process and figure out how to design around them. And in that kind of respect, what designers are doing is really tweaking, for the most part details. All right, designing for injection molding, what draft angle should I use? What radius should I use on sharp corners to round the corners? Things like that. So design guidelines along those lines. Do this, don't do that kind of design rules. And then there's also feature dimensioning sorts of design guidance. So in other words, if you want to design snap fits, these are the kind of dimensions that you should use. Again, focus mostly on the design details, right? That's what I call restrictive design for manufacturing, or design for additive manufacturing. The opportunistic design for additive is what I think is much more interesting and is really the distinguishing characteristic here. Because we have, shape complexity, material complexity, functional complexity, etc., there's a lot of new things that we can do. And really the challenge for the designer is to figure out how to take advantage of these unique capabilities to solve their problem in ways that haven't been explored before, right? I use this fuel manifold example from Olaf Diegel as an example. You don't get that design by tweaking the details on your conventional, let me gun drill from a block of metal kind of approach to a fuel manifold. Right? This is a clean sheet design. You've got to think in terms of designing for additive to get that sort of a result. Okay? In terms of the design opportunities, we can kind of categorize them as complex geometry, custom geometry, multiple materials, and node tooling. And there's a number of consequences for each one of these things. One of the big advantages that a lot of people talk about is part consolidation, right? So you can replace 4 or 5 injection molded components with one additive polymer component, or 10 metal parts that are welded and brazed together with, one metal powder bed fusion parts, things like that. Right, and that's really important. But there's a lot of other advantages here. And when we think about part consolidation, you're eliminating tooling. You don't have to design tools and fabricate tools like injection mold. You don't have assembly operations either. You don't have to worry about assembly tooling, right? Then if you are really effective, the performance of your device, your integrated device, can be a lot better than those modules or components that are built of several different conventionally manufactured components. So, and since we don't have, really no tooling is required, lot sizes of 1 are possible, short lead times. Again, you don't design and manufacture tooling, but that also enables you to do distributed manufacturing. You're not reliant on a central facility where you've invested all that tooling, so you can do manufacturing locally on street corners and things like that. All right. There's a lot of things I could have talked about, a lot of good research, a lot of good results, but let me move on and just say that design for the additive process itself is necessary, but it's not sufficient. Because most production parts are not the result of one manufacturing process. In fact, if you look at metal powder bed fusion or metal additive manufacturing in general, there's a lot of additional steps. So you really have to design for the entire manufacturing process chain, because your end result is the sum of all of these different pieces, right? So metal additive, typically you do a heat treatment of some kind. You've got to remove support structure. You probably want to do some overall finishing, or at least finish machining of your important surfaces and things like that. And so the structure of that process chain is important. What processes are in it. The sequencing is important as well, because there's implications for changing the orders here. If you remove support structure before you heat treat, your part's probably going to deform a lot. If you heat treat right on the build plate without removing supports, You're probably going to maintain the desired shape a lot longer, do that stress relief, things like that, remove residual stresses, get a better result. The point simply is that you've got to design the entire process chain and the part. They all have to be compatible. That's a lot of work, but you also have incredible design freedoms in each step along the way. Okay? Just to illustrate that, this is a project that was actually done in one of my graduate classes at Georgia Tech a few years ago to redesign a bike stem, the thing that holds the handlebars onto the frame. We'll assume that this is tie 6.4. We have some loading conditions, and the students did generative design using Fusion 360 and generated that optimized shape. That's not the final design. There's still a lot more work that had to be done. That's the final design. Okay, and they did a really good job of going through lots of details. So they did the opportunistic design, right, the generative design, and then they did a lot of really good restrictive DFAM as well. I won't go through all the details here. A big part of what they did is they said, all right, we're designing this lightweight, stiff bike stem. We're going to assume production manufacturing. And what that means is we want to make as many parts in the build chamber as possible. So let's orient the parts vertically so we can put a lot in the build chamber, or in the putter bed. But if we do that, that has implications on the part design. Okay? So what we don't want to do is in the lattice structure, we don't want support structures, holding each of these little struts in place. So all of those struts have to be self-supporting. So all of the struts had to be tweaked a little bit. Rounds were added everywhere, things like that. And then they made some other design decisions based upon minimizing support structure. So these purple things, blue things are the support structure that's supporting the overhangs here. And they made some other decisions about using gusset supports in the big cylindrical areas. Those surfaces had to be machined anyways, tight surface finish requirements because of the mating surfaces. And so all of these things were considered. These students also knew a lot about machining, so they did detailed machining process planning and simulation and determined machining times and build times and all that so they could estimate overall part costs. So they really did a good job of putting that manufacturing process chain together and designing each and every step along the way. Okay, this is a type of construct here. Sorry for the animation. That I call a process chain map. It basically relates design requirements to the different steps in the process chain. The green check marks indicate which process affects which design requirement. And so what you want to see is you want to see all green checks on the right-hand side. And if you don't, then that means you've got to make some adjustment in your process chain. Okay? All right, so that's kind of an overview of that idea of design for the additive manufacturing process chain. Now when we want to tie that to some of the technical design and technical design research, we can take a look at the structure of that process chain and say, all right, for this design problem, I have a bunch of technical requirements, functional requirements I have to meet, and then I want the manufacturing processes to be fast, less expensive, but give me a good enough result. And so that, to me, sounds like a multi-objective design optimization problem, right? And so we can actually use multidisciplinary design optimization, MDO techniques here to formulate and solve a large, comprehensive, integrated design problem where we can decompose the overall part process chain design problem into, again, a functional part design sub-problem, powder bed fusion process design, heat treatment process design, finished machining or support removal process design, and finished machining. We can use surrogate models and stuff like that for each of these. But the point is that we can start with this sort of abstract idea of design for the manufacturing process chain and actually apply very good, well-developed design theory and methodology kind of tools here. We've done this for a few different examples. One is that bike stem. I'll just do size optimization, not with the lattice structure and stuff like that, just to illustrate that we can explore that design space defined by, in this case, we had 3 objectives: deflection or stiffness, build time, and then part weight or part volume. And then, explore all the different combinations of the implications of those 3 objectives. And because we have 3 objectives, we can draw a ternary diagram like this, where blue indicates low overall objective function values, red indicates high. And then we can kind of sample the design space here, and we find that point A up at the top in that blue area, blue is supposed to be good, right? But it's really an infeasible design, and much of the rest of the design space looks like this. So the overall, or the outside shape is pretty much constant. We want to minimize deflection, maximize stiffness, so it's a pretty big cross-section. But the overall cross-sections inside vary a lot as we go from, for example, point C down to E and F down here. The point simply is you can, again, start with that overall design for the manufacturing process chain kind of problem formulation, apply MDO methods, and then do design exploration and optimization from there. Okay. Now on to sustainability kind of considerations. So I was fortunate to be part of a group that recently published a paper in Nature Sustainability on a vision for sustainable additive manufacturing. A great group of co-authors here, and I'd like a special shout out to our fearless leader, Serena, who really drove the development of this paper and the development of the ideas. So thank you, Serena. All right. So some of the ideas here, I'll go through just a set of bullet items that are sort of common statements about additive manufacturing and sustainability. Some are supportable and some are not quite. So first one is AM eliminates manufacturing waste. AM reduces the carbon footprint of parts manufactured. AM eliminates transportation of parts and supply chains. AM can make use of recycled, bio-based, or biodegradable materials. AM enables lightweight parts. AM enables significant part count reduction, that part consolidation I talked about earlier. No tooling, fewer manufacturing and assembly operations. And finally, AM enables part repair and refurbishment. Okay? All right. Some of those are true statements, and some are, well, maybe fudged a little bit. So the top 3, there should be an asterisk after that saying, well, sometimes, right? And I'll go through a couple of these. So there have been some really detailed LCA, life cycle assessment studies of additive manufactured parts, and this is a chart showing a particular set of examples that are polymer parts. I won't go through all the details here, but what you see in the middle, MEX, it's material extrusion or 3D printing, 1, 2, 3, 4, with 2 different materials. For the same process, different materials, maybe different printers, the energy usage is completely different. And in fact, this is really unacceptable. There's no reason a material extrusion machine should use that much energy. But if you just take a look at, reduces carbon footprint, right? Well, yeah, no, not in all cases, right? Another kind of example, and this is for metal parts here, carbon footprint per kilogram of material processed is actually maybe not such a good measure. But again, highly variable. Casting, extrusion, roll forming, wire drawing, conventional processes, the bars aren't so long. We start going down here to metal additive manufacturing, and we see that, well, no, the carbon footprint per kilogram of material processed is actually really significant. And in large part, that's because the lasers that are used in these machines are not very efficient. Back when I started in the mid-90s, lasers were 1% to 2% efficient in terms of power out versus power in. Now they're 25%. Huge improvement in laser technology, but still maybe not enough. The big bar here is for aluminum. Aluminum is a real shiny material. Lasers don't couple well with aluminum powder. The other thing to consider is powder is incredibly energy intensive to produce. So atomizers, melt and then vaporize essentially metal. Just think about the process here, right? You're casting large ingots of metal. You're then shipping them to a facility that has atomizers. You're remelting all that metal and then generating powder with it, and then capturing it and sieving it, and it's just, the whole process doesn't make a lot of sense, but regardless. Now when we look at the real positive side and some of the really creative solutions that people have developed, I really like this example of a solar-powered sand printer. This is a master's student at the Royal College of Art in London who came up with this idea of using solar power, so a solar power collector, powder bed fusion, so this is a vat of sand powder, and it takes the solar energy, makes a beam out of it, and then rasters the beam in the top layer of the sand bed to then produce essentially a glass part. Okay, very low carbon footprint here, right? Other people have been really creative about material development. So we see salt shakers made from salt up here. This filament is actually made from wine, or it's actually grape skins. This sample over here was 3D printed at Singapore University of Technology and Design. It's composed of cellulose and chitin, so bio-based, biodegradable sort of material, and that really is about 5 meters tall. So very good material. So really good opportunities for developing new, much more sustainable kinds of materials. Another one of the bullet items there was AM can be used for repair, refurbishment, and things like that. Well, directed energy deposition processes are used probably more for repair than they are for part fabrication. This just illustrates a few different examples of depositing a millimeter or two of metal material onto a worn a part of various kinds. You see shaft applications here, or a bladed disc kind of application as well. All right. So in our paper, we provide a series of statements or proposals for how AM can be made more sustainable. And again, like a lot of things, if you try to tweak the machines or the processes or the materials a little bit, you're really not going to make big changes. But if you think more systematically and more systemically, you can make really, really big impacts here. So look for opportunities to design for part repair, design for upgradability, refurbishment, remanufacturing, things like that. Look for opportunities to not use conventional high carbon footprint sort of materials, but opportunities like I just showed with biodegradable or bio-based sorts of materials, instead of designed for recycling. And again, always designed to take advantage of AEM's unique capabilities. Okay? We provide this overall sort of idea about an ideal scenario, okay, that covers everything from, the raw materials, whether it's bio-based or biodegradable, or coming up with a new way. I'll get out of the way, you can take pictures. Coming up with a new way to make metal powder would have a huge impact as well. Printer design, part design, how all those integrate together. With the process design and the actual 3D printers themselves, how energy efficient they are, what their characteristics are, and then from the printers into the production system overall and the part and product life cycle. So again, the scenario is trying to tie all that together. Remember that one of the bullet items was, hey, AEM eliminates part transportation costs. All of the trucks in that schematic indicate something is being transported. So again, not exactly. But again, we have the scenario here. You can take a look and study it further. Okay? I am probably running out of time a little bit. I don't know, how are we doing on time? Okay, no one cares. Great. I'm going to keep talking. Now, I've got two more topics here. I'll go through them fairly quickly. So I've said repeatedly, we want to take advantage of the unique capabilities. And really what's key there is to look for changes in part design and product design that can have a really huge impact. And to me, the thing that really has a huge impact is product architecture design. That's indicated by this e-bike, this motorcycle here. But first, a real extreme example. Now, GE, and in particular GE Aerospace, has been one of the leaders in designing for metal additive manufacturing. And as a demonstration, they redesigned this turboprop engine. There's a conventional design. And here's their additive manufacture design. They claim to go from about 850 parts down to 11. Okay? That's an order of magnitude in part reduction. And so this isn't just applying the Boothroyd-Dewhurst design for assembly guidance of, well, if two parts are connected and they're the same material and they're not moving relative to one another, you can maybe consolidate them. You can't just apply that and then get an order of magnitude decrease in part count. You've got to really do clean sheet design. And that's what GE did. All right. So they not only can really greatly simplify the factory floor, they get better performance better performance and probably longer life, things like that. Of course, central to product architecture design is this idea of am I modular, am I integral, where on that spectrum are we? There's a role for both. But I would argue that in terms of applying additive manufacturing, if you have a modular architecture, each of your modules could be highly integrated and very efficient from a part count perspective. A little bit more about this 3D printed motorcycle. So this is an e-bike, electric motor-powered motorcycle. A couple things that are really novel about this. It consists of 15 3D printed parts. And that includes the tires, wheels, seat, frame, everything. Well, everything except the electric motor, the battery, and the control electronics. But everything else is 3D printed. And when I say 3D printed, I mean thermoplastic material extrusion kind of 3D printed. Okay? One thing to notice about this, this is a hinge that allows you to steer. Okay, it's not the spring. It's not a spring that's part of the suspension. In fact, there are no suspension components in here whatsoever. Okay, but you get a suspension function because you have elastomer wheels. You've got honeycomb structures for the elastomer tires. Honeycomb structures in the wheels. You have this flexible bumper. It's basically a honeycomb structure that will flex underneath the seat, and the seat is elastomer as well. Plus, the whole frame is, it's ABS, carbon fiber reinforced ABS. So it does have some flex as well. But if you can eliminate entire subsystems, like suspension subsystems, you can get, you're changing the product architecture radically, and you can get tremendous part consolidation. All right. Now, from an engineering research or design research perspective, we can go back, look at the functions, look at, the relationship between function and form, and where do modules come from, and then look for opportunities for function sharing, function integration, and things like that. So we did just that, listed the functions out, listed the different components. I won't go through all the details here, but again, let me go. Yeah. So suspension gets replaced, and we get some function sharing. The overall architecture, there's no separate handlebar from the fork, from the steering mechanism. They actually did left and right sides, so the left handlebar is connected to the left fork, right hand, okay, and there's a hinge in between. So some novel design components, and then of course, going from a gas-powered motor to an electric motor, you get some function integration, don't need a separate transmission and things like that. So, you know, tremendous differences in architectures between conventional and this specially designed e-bike. Okay, and then more broadly, okay, got it. More broadly, you know, we can look at a whole set of industry examples. Interestingly, they're all in the transportation domain, but that's okay. So again, in aerospace, the e-bike, and then a couple of, you know, car and minibus sort of examples. And it turns out that these three are all thermoplastic material extruded designs, and then the GE motor engine is metal powder bed fusion. Okay. In each case, essentially the products resulted from clean sheet design, novel product architectures, novel approaches to design, and a lot of good insights in additive manufacturing that they could take advantage of. All right, now a few words about 4D printing. So 4D printing is 3D printing with the fourth dimension being time. So you have a shape change over time. So the Georgia Tech box over there was designed such that different joints were actuated at different times. And then this example, one of my favorite examples, Christina, thanks for sharing it, even though you know you didn't know you shared it with me. This is a solar panel deployment mechanism where the scissor mechanisms along the outside are shape memory polymer things that actuate to go from a folded to an extended configuration. And that opens up an origami interior where the actual solar panels are mounted. So just two different examples, sort of two ends of the spectrum in terms of complexity, but this is the idea. If we go back to this one, you know, the box started out as printed flat. Okay, right. So you could print that flat, you could print out 1,000 of them, ship them all stacked up, and then where they are needed, you put them in, or you heat them up, it actuates the shape memory effect, and they fold up into the desired shape, right? Solar panel, those go on satellites, right? You need something very, very compact to launch, and then you want it to deploy. So it's that sort of idea. So I've talked a lot about product architecture design and part consolidation. And so additive manufacturing has had a huge impact on you know, this idea of designing structures or structural components, right? With 4D printing, with utilizing the shape memory effect, we're actually designing actuators into our structure. And so if you think about conventional mechatronic devices, right, there's servo motors and bearings and shafts and bushings and set screws and lots of different components. If we can replace those with shape memory hinges, we have a tremendous simplification of the design. Tremendous part consolidation. So long term, the future is 4D printing is going to do for mechatronic devices what 3D printing has done for structures. That's my prediction. You know, take it with a grain of salt if you want, but we'll see if it comes true. And then finally, when you look at the 4D printing or the shape memory device literature, you see very simple components for the most part. We developed this new material, we're going to print a strip of it and look at folds, right? Christina's example with that origami solar panel is one of the notable exceptions. But the point is there's been a whole bunch of these simple components that have been designed and engineered. We know how they behave. Right? If we had an overall design synthesis capability that said, hey, here's my problem specification in terms of start with that shape, give me that shape eventually. How many different ways of combining these components might you come up with that could fulfill that requirement, right? So one of the topics that we're working on at A-STAR in Singapore is this idea of a general design method for 4D printing for morphing and deployable structures that's based on this idea of a design library and matching that with problem specification. So we'll see how all that works. Yeah, I forgot. Okay, all right. So we need this thing to bend. Okay, let's use a bending cylinder. We need that stretching or that extension. Let's use a scissor mechanism to then go interrogate an entire workspace in a robot arm sort of fashion. Okay. To wrap up here, I wanted to introduce the whole idea of design for additive manufacturing, contrast that with design for manufacturing, emphasize again that we have some unique capabilities, and the challenge to achieve the maximum benefit is to take advantage of those unique capabilities. But do remember, we got to design for the entire process chain, not just one process. We took a look at, kind of the pros and cons and good and bad characteristics of AM relative to sustainability. And then I had a few words about product architecture, design, and 4D printing. With that, thank you for your attention. I hope you've learned something. And a final note and a shameless plug. I understand that this is a really good resource if you want to learn more.
Thank you very much. Thank you very much for that wonderful presentation. I'm sure there are some questions. We take time for some questions.
Okay.
Who's got a question, please? No questions. Could not be. Come on.
You know professors like questions. And don't let
Serena,
me off the hook.
Yeah.
Serena.
Okay, thank you for this wonderful overview, for the insight you provide us. I have maybe a tricky question for you. Is there something you have not yet seen in additive and you would like to see developed as a design, from a design point of view? Is there something missing from your point of view?
Yeah, I'll give you two quick answers to that. One is, I want someone to come up with metal powder production that doesn't involve the conventional, metal fabrication workflow, because again, it's highly, highly inefficient. But the other thing I want to highlight is, let's assume that we do solve that problem. Just think about fabricating an engine block using a laser that's 100 microns in diameter. You can scan as fast as you want. It's still going to take you days and days to fabricate that. And at 50 to 100 euros per hour, that's more money than I have in my pocket, okay? That's really expensive. And why isn't additive used in the automotive industry, but it is in medical and aerospace? It's because those industries are not nearly as cost sensitive. So what we need is new technologies that allow us to fabricate cross sections at a time in metal. Right? So we've got to get away from, one laser scanning or 10 lasers scanning. We've got to get to 1 million beams or something equivalent to that to do what stereolithography did from laser scanning to DLP, mass projection, right? We need the same kind of technology for metal additive, and that'll have a huge impact. Thank you. Christina.
Thanks for the nice presentation. Of course, I have a question on the last point, 4D printing. Mm-hmm. What do you think are the biggest challenges to be able to reach the goal that you set of replacing standard things like hinges with a 4D printed hinge?
Yeah, that's a great question. If I have the chance, I'm going to turn around and ask you the same thing, because you may have more insights. But I would say that the materials really need to be greatly improved. Yes, we get the shape change, but the forces and the torques that are being generated are very small. So, can you really launch that solar panel deployment mechanism and have it operate? And, maybe not so much. So, I think materials is really, really key here. And then, the other, again, I talked about a design method here. I really think that we have a tremendous opportunity to come up with new ways of synthesizing devices that span from, simple components to origami kind of structures to compliant mechanisms, and a continuum among those. Okay, thank you.
Thank you, Professor, for the very nice talk and variety of things which are going on in this area. I was particularly interested in the 4D printing space, again, connected to the previous question as well. In one of your slides, you had hinted that we could use magnetic fields and some mechanisms for triggering. The thing which is interesting about mechatronics is you have electronic control. Can you share a little more about what mechanisms can we use for controlling structures like this?
Sure, yeah. So kind of as shorthand, 4D printing is shape memory effect. Well, we don't have to limit ourselves to just shape memory. We have residual stresses, we have shape memory effect. Plus, if we add electrically or magnetically active particles or things like that into the material, we can use additional fields to try to, get improved performance. So again, there's a whole spectrum of technologies that we could bring to bear, and you want to add those additives to get better mechanical properties, get faster actuation, more repeatable actuation, more forces, things like that. So again, now. We also have a controls issue here, right? So right now, I'll just contrast that with the examples that I showed where we put the entire device into a vat of hot water and the heat in the hot water actuated the shape change. We really want to be able to locally control the actuation and control it and maybe build sensors in there as well so we can do feedback or closed loop control of all of this. When we start adding electrically and magnetically stimulated, well, we've just really complicated the whole device now. And so there's a trade-off there. So these are all sort of trade-offs and considerations that really have to be explored, but plenty of opportunity for novel design ideas to take advantage of the best aspects of the technologies, but achieve good trade-offs among the competing objectives. All right.
Okay, I think everything was absolutely clear. So again, thank you very, very much for the wonderful presentation. Thank you. And now we have coffee break until 3:15, and we all meet here at 5:30 for the closing ceremony. Thank you very much.
Thank you.